Hello friends, so welcome to the course of Power Electronics in the Electrical is Easy channel, and today we are going to start a very important topic, which is the construction of power diodes. Now this could be one of the most important topics in power electronics because the understanding of most of the devices starts with the understanding on the construction of power diodes. Therefore this topic is very important for understanding even other devices like SCRs etc., which play a very important role in power electronics. Right? So whenever we talk about power diodes, what is the most important characteristics? So the power diodes have quite large power ratings. Now what is the meaning of this large power rating? Now the first point is that the power diodes can conduct several kiloamperes in the forward direction with very less power loss. That is very important. Now for example, you are having a diode here like this, right? So this is the anode and this is the cathode, and if you are forward biasing by putting positive polarity in the anode and the negative polarity in the cathode, you know that there is going to be a forward current which is going to flow, right? You know that whenever this forward current is going to flow, if I replace this diode by its model, you know that there is a resistive component also involved here, right? So when several kiloamperes are going to flow, there might be a lot of power losses also associated with that. But in a power diode, you want it to have high current conduction in the forward direction, that is several kiloamperes, but with very little power loss. Okay, so that is one important point. Another important power rating associated is that it should be able to block several kilovolts in the reverse direction. In fact, today we will be discussing about this, of how it can block several kilovolts in the reverse direction. Now in power circuits, you know that in the reverse condition, for example, you know that in a power system, you know that the voltage is going to be alternating. So in the negative cycle, if you are having a diode which is connected there, it will experience this reverse condition. The diode should be capable of blocking this reverse voltage without getting damaged. Okay, so that is the basic idea of blocking several kilovolts in the reverse direction, that is in the reverse cycle. And also it should have good heat dissipation characteristics. Naturally, when a high amount of current is going to flow, there are going to be losses associated, but it should have good heat dissipation. So the question is how it is going to block this several kilovolts in the reverse direction. So how to get large reverse voltage blocking capability? That is the question now. So before understanding that, you have to have a basic understanding of something which is called impact ionization. Impact ionization. So you can see that in the right side, I have already put a simple diode here, which you have already seen. So this diode, you can see that this is the P side and this is the N side. And let me just take a different color now. Okay. So in the P side, I have put negative. The P side I have put negative, and the N side I have put positive. That means this diode is under the reverse bias condition. So naturally you will have a depletion layer. Okay, so the depletion layer, in one side you are having positive charge and one side you are having negative charge, and this region of depletion region is void of any charge carriers. That is the basic idea we know. So we know that in this condition there will be an electric field which is going to exist within the depletion region, right? So I have marked that direction. The electric field will exist from positive to negative, so that I have called it as E depletion. So this is the electric field which exists in the depletion region due to these charges. Okay. Now, due to this applied voltage, which is positive in this side and negative in this side, the applied voltage is positive in this side and negative in this side. Because of that also there will be another electric field. So you can see that the electric field applied is aiding the electric field which is in the depletion layer. So that is an important point. The electric field which is applied, the electric field created due to the applied voltage supports the electric field in the depletion region. So this is one important point that you have to remember. Now you know that there might be some electrons etc. which are generated due to thermal conditions, right? Due to temperature, there might be some electrons which are getting created. So for example, you have an electron here, okay, which is created. And you know that these types of charges actually constitute the reverse saturation current, right? For example, you are having an electron here, and what will happen to this electron in the electric field? It will experience a force, right? The electron in the electric field will experience a force, right? So naturally, if you see the polarity here, the electron has polarity like this, you know that it will experience a force in this direction, right? It will experience a force in this direction. Okay, so this E depletion will accelerate the electron, Okay, we need not tell electron, actually we can also call it as the charge carrier. Electron, hole, anything, we can just generalize and call it the charge carrier. Anyway, for this case we are taking the electron, so it will be accelerated in this particular direction from left to right, natural. Okay, now because the electric field applied supports the depletion region electric field, this acceleration will give, this acceleration which is already obtained by the electron will be magnified, right? The electric field which supports, the electric field applied supports the electric field created due to the depletion region, and the acceleration that the electron has got will now get multiplied, because this electric field, applied electric field also will be applying a force on the electron, right? So that acceleration, due to that acceleration, what will happen? You are having other silicon atoms also, right? You are having other silicon atoms also here. And this is the electron which is now accelerated by both the depletion region electric field and the applied electron field. So it will have sufficient energy to go and knock some other electron from some other atom here. See, just because I have not shown anything here, it does not mean that inside the crystal lattice structure there are no other silicon atoms. There will be a lot of silicon atoms and all, right? So this electron might go and knock off this particular electron. It might. So this electron will get knocked off. Okay, and now this electron will get accelerated due to these two fields. So this might go and knock off some other electron, right? And this might go and knock off some other electron. Okay, so this process in which this electron is going and knocking off another electron from some other atom is called impact ionization. Okay, it is called impact ionization. And if this continues, that is continuously electrons are getting generated in the depletion region, naturally you know that the reverse current is going to increase, right? And this large increase of reverse current might damage the device, and this type of breakdown, is actually called avalanche breakdown. Okay, so this type of breakdown is called the avalanche breakdown. So I hope the concept of impact ionization and avalanche breakdown is clear now. So now the question comes, how to get large reverse blocking voltage? Okay, I've told you to understand this, you need to understand this. So the solution here is to have a wide depletion layer. Okay, so how does the wide depletion layer help? That is the next question. A wide depletion layer actually allows us to restrict the electric field below the impact ionization level. Naturally, if you are having a wider electric field like this, wider depletion region, you know that the electric field will be less. As you increase the distance, naturally the electric field will come down. Therefore, this initial acceleration that the electron gets due to this electric field in the depletion layer will be reduced, right? So when the width of the depletion layer increases, the electric field which is developed in the depletion layer decreases. Okay, and due to which the initial acceleration is less. So compared to the previous case of a smaller depletion region, this electric field applied must have a higher value in order to provide sufficient acceleration to this electron to go and cause this impact ionization. I hope I am clear. See, the original electric field which was used for the acceleration itself has reduced, right? So naturally, as compared to the previous case, you should have more applied electric field or more reverse bias voltage should be applied to get the avalanche breakdown. So that is the idea. So when you have a wide depletion region, you restrict the electric field below the impact ionization level. So to get the same breakdown, same avalanche breakdown in the diode, you should have a much higher reverse voltage which is applied. So I will write down that here. So in this case, the reverse voltage will have to increase to cause the avalanche breakdown. Now, simply increasing the the depletion layer width will not help you. Naturally, the charge carriers which are existing inside the depletion layer also should be less. See this positive, negative which I have shown here, those should also be less. Only then that the electric field will be reduced, right? So, the space charge density also should be low. Sorry, I have just written about this a little bit. The space charge density should be low. This is low to get a wider depletion layer for the same electric field. Okay, so naturally, if you have less charges, if the doping is very less, you will have very less charge carriers here, right? Very less charge carriers. So to produce the same electric field, you will get a wide depletion region. Okay, so once these two conditions are met, you know that you are naturally going to get a higher reverse blocking voltage. So that is how the reverse blocking voltage increases. Okay, so you have understood that to get large reverse blocking voltage, you need wide depletion region. So the question is how you are going to get this wide depletion region. Okay, so the question is how you are going to get this wide depletion region. So there are two solutions here. Let us see. So in the solution number 1, what we can do, you use a lightly doped PN junction. So in the previous video itself, I have shown you the width of the depletion region. The width of the depletion region is inversely proportional to the doping. Right, that we have seen in the previous video. So as the doping decreases, the width of the depletion region will increase. So the solution number 1 is use a lightly doped PN junction. So you are using less doping, width of the depletion region increases. So if width of the depletion layer increases, the breakdown voltage, the reverse breakdown voltage would increase, right? So problem is solved. The depletion, so these are the points that I already explained. The depletion width increases with less doping. So we can create a sufficient depletion layer using proper doping. Okay, if you properly design the values of the doping, you can create a depletion layer of sufficient width which can provide enough reverse blocking capability. But there is an important limitation here. The important limitation here is that your objective of creating a power diode, or a objective of a power diode, is not only do some reverse blocking, right? I have told you it should be able to handle kiloamperes of forward current, with less power loss. This is the next important characteristic. Right? It's the first, in fact, this was the first characteristic. It should be able to conduct a lot of forward current with less power loss. But the problem with less doping is that the lighter doping, when you are having lighter doping, you are having less charge carriers, right? When you are having less doping, naturally the charge carriers are less. So when the charge carriers are less, see here, the charge carriers are less. So naturally the conductivity of the material, right? The conductivity of the material will decrease. Right, when the conductivity of the material decreases, you know that the resistance of the material will increase. So for a particular value of forward current, if you use a lightly doped PN junction, because the resistance value is very high to the forward current, the power losses will increase. The power loss will increase in the forward conduction. So I hope I am clear. Lighter doping means less charge carriers. Less charge carriers means lesser conduction. Lesser conduction means higher resistance to the forward current flow. And the higher resistance causes higher forward conduction loss. That I have already explained here, right? So higher resistance causes higher forward conduction loss. And for a power diode, this power loss at rated current will be unacceptably high. So you cannot use a power diode with such high amount of power loss. Therefore, this solution number 1, to increase the reverse blocking capability by using a lightly doped PN junction, is not a good solution. So now what is the problem here? The problem was the during the forward conduction, the power loss is very high. That was the problem, right? So what can we do to do the solution? What is the solution for this? The solution number 2, the solution is forward loss can be reduced by increasing the doping, right? So you needed high reverse blocking. So you needed the breakdown voltage of the diode should be high, right? So what did you do? You reduced the doping. This is the sequence. you reduce the doping, and when the doping was reduced, the depletion width increased, so you got high breakdown voltage. But what happened here? Due to the fact that the doping has reduced, the charge carriers are less. The charge carriers are less, right? And due to that, the conductivity was less. Conductivity was less. Conductivity less means resistance is high. So you had power loss will be high in the forward conduction. So to reduce this loss during the forward condition, that is the forward loss, now you can reduce by increasing the doping, right? So if the doping increases, naturally the charge carriers will increase, right? The charge carriers will increase. And if the charge carriers are increasing in a material, you know that the conductivity is going to increase. Conductivity increases means resistance is low. Therefore, in the forward conduction, during forward conduction, the power loss also will be low, right? But the problem here is that once you increase the doping, the reverse breakdown voltage reduces, right? So once you increase the doping, what happens? See, when the doping is reduced, the breakdown voltage increases. But when you increase the doping, what will happen? I'll write it here. When the doping is increased to reduce the forward conduction loss, the VBD voltage at breakdown will decrease. So these two solutions are contradictions. The problem is that both these solutions are contradiction. You are trying to increase the breakdown voltage, but at one point you are getting high forward conduction loss. And you are trying to reduce the forward conduction loss, but you are reducing reverse breakdown voltage. So both these solutions are contradictions. So what is the solution? There is a very smart solution to this. Great people have invented that solution. It is the introduction of a layer of lightly doped N material. Okay, it is introduction of a layer of a lightly doped N material, which is called drift layer of sufficient thickness in the PN junction diode. So by introduction of the drift layer, you will get high. So I'll write it here. So the introduction of the drift layer, I'll write it here because there is a photo which is going to come below. So the introduction of the drift layer, what it will guarantee? It will help VBD will go high, that is the reverse breakdown voltage capability will go high, and the forward conduction loss also will be very less. So that is the basic idea of introducing a third layer in the PN junction diode. This is called the drift layer. So in all power diodes, you will have this drift layer. So basically you are having an N minus, you are having basically a PN junction diode, right? So this is your P side, this is your N side. In between, you are having another layer which is called the drift layer. This is called the drift layer. And this drift layer, which is of N-type material, will be very lightly doped. It is a very lightly doped material. So to show that it is lightly doped, you put a minus sign here. So this shows that it is lightly doped. And the P and N side will be heavily doped. Naturally, it's a power diode, right? You need a lot of charge carriers. So you will require a very high amount of doping as compared to signal diodes, right? So that is why you are having the plus sign of P side and N side to show that they are heavily doped. Okay. So if you see roughly the values, for example, this is the P side, so this is the anode, and this is the N side, this is the cathode. So this is the N side, right, and this is the P side. Okay, so this is the P side here, and this is the N side, and this is the drift layer. This is the drift layer. So for the N side, roughly the doping, so because the N type doping, you call them as donor atoms also. So there is a way to write this. So ND, okay, doping concentration of the donor atoms in the cathode, okay, which is roughly 10 power 19 per centimeter cube. Okay, and for the P side also, because P side doping you do acceptor atoms, so this is called NA, I'll just NAA, that is also roughly equal to 10 power 19 per centimeter cube. 10 power 19 per centimeter cube. Whereas for drift layer, the drift layer, naturally it is also an N-type material, so it will also have donor atoms. So ND of the, we'll just use small characters here. And here also we'll use small character. ND of the drift layer, that is the concentration of donor atoms in the drift layer, will be roughly equal to 10 power 14 per centimeter cube. You can clearly see the drift layer is orders of magnitude less than the P side or the N side. The doping of the drift layer is orders of magnitude less as compared to the P side and N side. Now in a low power diode, like a signal diode, for example, like a signal diode, this drift layer is absent. See, when we studied basic PN junction, I never told you about this drift layer, right? But in power diodes, this drift layer will be there. Drift layer is absent. So, in the next video, we will see the reverse bias condition as well as forward bias condition while introducing this drift layer. Okay, so that is very important in understanding how this drift layer is going to give you high reverse breakdown capability and less forward conduction loss. And these two topics are very interesting. Okay, so that we'll see in the next video. So I hope you have understood whatever I have tried to explain in this video. So till I see you in the next video, it's me Varun signing off, and have a great day. Thank you.
Now that the video is over, please stay with me for 30 more seconds. Now the vision of this channel is to create a repository of good quality videos with crystal clear explanation regarding various topics related to electrical engineering. Now if you want to help me spread the word, please share this video with anyone interested in these topics. The second thing is that for me, education is a two-way process. Therefore, if you have any doubts or suggestions regarding any of the videos or regarding the channel, please put them in the comments below. We can have a healthy discussion, and that way we can build a strong community of electrical engineers. So that's it for today's video. So till I see you in the next time, it's me Varun signing off, and have a great day. Thank you.